Good morning, my dear students. Unit 4 Semiconductor. Last session we have discussed about origin of energy bands, classification of solids. In this session we are going to study about different types of semiconductors, intrinsic semiconductors, and density of charge carriers, Fermi energy of intrinsic semiconductors. Before going to the next topic, I want to brief about the last session. So here you can see the different types of solids, insulators, conductors and semiconductors and their comparison. And we know that in insulators all the electrons are tightly bounded and we require more energy for getting the free of the electron. And we know that the energy gap is always greater than 9 electron volts, and examples are wood, mica, pure water, plastic and glass. When it comes to the conductors, it consists more number of valence electrons, and these valence electrons are loosely bounded, and their energy gap is around 0 electron volts. Examples are gold, copper, aluminum, iron. So it requires very less energy for getting the free of the electron, and these electrons are the responsible for the electrical conduction in conductors or metals. You can see in this animation. So now come to the semiconductors. Semiconductors behaves intermediate between the both insulators and conductors because of the energy gap lies between the 0.1 to 3 electron volts. It is the intermediate value of insulator and conductors. Electrons are not free to move, but a little energy is enough to get the free of electrons. Examples are silicon and germanium. Low resistivity and high conductivity there for conductors, and for insulators high resistivity and low conductivity is there. But if you see for semiconductors, this resistivity and conductivity are intermediate between the both conductors and the insulators. Now we are moving to the next topic, semiconductors. Different types of semiconductors we can classify as extrinsic semiconductors and intrinsic semiconductors based on their purity. And most of the fourth group elements in the periodic table are intrinsic semiconductors. Okay, whenever you dope this fourth group elements with third group or fifth group elements, then we can get the p-type semiconductor and n-type semiconductors. Next, intrinsic pure semiconductors. Examples we already told, silicon and germanium. If you see here, valence electrons are there in s and p orbitals only, and these 4 electrons forms the 4 covalent bonds with the neighboring atoms. Here you can see the crystal structure of the silicon. Here one silicon atom is sharing these 4 electrons with another 4 silicon atoms by forming 4 covalent bonds. That's why it is forming the sp3 hybridization. Due to this, it has the diamond cubic structure. Okay. Next, if you see in silicon, crystal structure looks like this. It is a 2-dimensional. The same thing you can extend to the 3-dimensional. Then you can see the diamond cubic structure. Whenever we apply the energy in the form of heat or electrical energy, some of the electrons will be free from the lattice, and these electrons will move freely in the lattice. These are the random motion if you have not applied any voltage. See, similarly, hole also moves in the lattice, but hole movement is different from the electron movement. Here hole is moving within the bonding direction, within the bonding lattices only. Okay. Now if you see, whenever you apply the energy in the form of heat to the silicon or any semiconductor material, it generates the both electron and holes that you can see in the energy band diagram. Here same number of holes are generated by exciting the same number of electrons to the conduction band. These are the responsible for the conduction of electricity in semiconductors, especially intrinsic semiconductors. Both holes and electrons are majority carriers. Okay, here you can see whenever you apply the voltage for the intrinsic semiconductors, this electron is not in random motion. These are moving in one dimension or in one direction only. This is called drift of the electron. This, okay. So whenever you biasing the semiconductor material, all these electrons will get the drift velocity and moves from negative electrode to the positive electrode, gives the flow of current in the materials. Okay. Now we have to find the carrier concentration in intrinsic semiconductor. Carrier concentration is nothing but number of electrons or holes in a unit volume in a given band of energies. If you see here band of energies means valence band and a conduction band. We know that whenever you apply the voltage, it is generating the electron and hole pair, and equal number of holes are there in the valence band and equal number of electrons are there in the conduction band. That indicates in intrinsic semiconductor always N is equal to P, and it is indicated by the intrinsic carrier concentration Ni. Now we have to find this value, N and P values, then we will find the Ni value. Okay. Now how to find the N value? Very simple. First you have to find the density of energy, the number of energy levels per unit volume. Suppose I assume that within dE, between E and E plus dE energy levels, we assume that Z of E dE is the density of states, and it contains dN number of electrons. And this value is also depends upon the probability of finding the electron within these energy levels, and this f of E is highly dependent on the temperature. Now dN is defined as dN is equal to Z of E dE f of E. This is only for within the short range of energy levels. Now we have to extend this for the entire band. Here band means you have to take only the conduction band, because electrons are available in the conduction band. So we have to take N is equal to integration of this function, and lowest energy of the conduction band is EC, and highest energy of the conduction band is infinity. That's why we have written top of the band. Okay. Now we have to write the Z of E and F of E values, then you have to substitute the values in this equation, then we can find the N value. Here we know that Z of E dE is equal to 4 pi h cube 2m whole power 3 by t power 1 by 2 dE. This is generalized equation, but here we have to take for the electrons though, so we have to replace this m value with m star. Okay, and here energy is starting from the EC value, so this energy should be E minus EC, so that we replace the E by E minus EC, gives the Z of E dE, density of states within the energy of E and E plus D. Now we have to find the f of E. This is the function f of E is equal to 1 by 1 plus exponential E minus EF by KT, and for E minus EF far greater than KT, if you simplify it, then we can get f of E is equal to exponential EF minus E by KT. By substituting this Z of E and f of E value in the equation 1, after simplification this, we can get the N value is equal, N is equal to 2 pi m star KT by h square whole power 3 by 2 exponential EF minus EC by KT. This is a very simple derivation. Just you have to assume that E minus EC by EC is equal to X. Okay, general simplification. After that you have to apply the integration from 0 to infinity, because these limits will come 0 to infinity, because the limit of E is EC to infinity. Okay, then for easy writing and remembering, we can write the same equation in terms of N is equal to NC E power minus EC minus EF by KBT, where NC is this value. So this is the equation represents the number of holes per unit volume in the conduction band. Similarly, we can find the number of holes in the valence band. But the important differences are here. Instead of f of E, we have taken 1 minus f of E, because the probability of finding either hole or electron is equal to 1. That means probability of hole plus probability of electron is equal to 1. Therefore, we know that this is the probability of electron. Therefore, 1 minus f of p gives the probability of finding the hole. Understand? Now, p, we have to take the integration from bottom of the band. That we know that it is a lower the value. This value may be minus infinity. Okay. And maximum energy of the band is EV. Understand? So now, we can write the Z of E d is equal to 4 pi hq to ms star. Here ms star is the effective mass of the hole. Then find the 1 minus f of e value. Okay, then you substitute this value and this value in the above equation. Then we can integrate the within the limits of minus infinity ev. Then you can get the p value. P is equal to 2 pi ms star kt by h square whole power 3 by 2 exponential ev minus ef by kt. Therefore, P is equal to NV e power b minus EF minus EV by KBT is the number of holes per unit volume or density of holes in the valence band. Okay, so you practice this one as a assignment, derivation of the P. Okay, next intrinsic carrier concentration. We already know that N is equal to P equal to I. Therefore, Na square is equal to Np. Then substitute the value of N and P. Then we can get Na is equal to 2 pi kt by h square whole power 3 by 2 ms star whole power 3 by 4 exponentially minus Ez by 2 kt. Here we can represent this as a constant parameter. Then we can simply write Na is equal to a exponential minus Ez by 2 kt. This is a intrinsic carrier concentration of the intrinsic semiconductor. Now we have to see the Fermi level and the effect of temperature on the Fermi level. Understand? And also effective mass. If you see, we know that in the intrinsic semiconductor N is equal to P. By equating this, after simplification, we can get the EF is equal to 3 kt by 4 log of ms star by m star plus EV plus EC by 2. And here we can see that this Fermi level is highly dependent on the temperature and also ratio of the effective masses of the hole and electron, and ideally we can take m star is equal to ms star. Okay, at this condition we can see that EF is equal to EV plus EC by 2 at the center of the conduction band and the valence band. But practically this is not the constant value. These are not the equal. So for ms star greater than m star, we observe that the Fermi level is increasing. For ms star less than m star, the Fermi level is decreasing with respect to the temperature. Thus, the Fermi level EF is located in the middle of the forbidden band in case of the ideal intrinsic semiconductor only. Now, electrical conductivity of intrinsic semiconductor. We know that electrical conduction is in the semiconductor is due to both holes and electrons, and we know the electrical density of electrons, density of current in intrinsic semiconductor, we can write Jn is equal to NeVd. Similarly, with due to the holes, we can write Jp is equal to Pe mu He. And the total electrical conductivity, you can write J is equal to Jn plus Jp by substituting these values, and we know that J is equal to sigma E. Therefore, the electrical conductivity sigma is equal to Ne mu E plus Pe mu H. And we know that for intrinsic semiconductor N is equal to P is equal to Ni. Therefore, by substituting this value in this equation, we can get sigma is equal to Nie mu E plus mu H. This is the electrical conductivity of the intrinsic semiconductor. Since we know that Na is equal to A exponential minus Ez by 2 kt, by substituting this value after simplification, we can get the electrical conductivity is equal to B exponential minus Ez by 2 kt, and resistivity will be rho is equal to C exponential Ez by 2 kt. Okay. So in this session we have discussed about the intrinsic semiconductor, types of semiconductors, and density of holes, density of electrons, derivations, and also electrical conductivity of the intrinsic semiconductor. Students, please take these three as the assignment for your better understanding. Get back to next session. Thank you.